Section 3.1, solve systems of equations by using graphs and tables. Please write down the essential question. How do I solve systems of equations by using graphs and tables? Who uses this? Winter sports enthusiasts can use systems of equations to compare the costs of renting snowboards. System of equations is a set of two or more equations containing two or more variables. On the graph of the system of two equations, the solution is the set of points where the lines intersect. So for example, if I have two lines that intersect, there is the solution, and the solution is a point which is an ordered pair, x, y. I'm going to use substitution on example 1 to determine if the given ordered pair right here is a element of the solution set of this first equation and of the second equation. How we're going to do that is we're going to plug the 1 in for x and the 3 in for y. So in the first equation, we have 1 minus 3 times 3. Does that equal negative 8 is what it's asking. Well, that's 1 minus 9. Sure, 1 minus 9 is negative 8. That is a true statement, meaning 1, 3 is a solution to this equation. Now, let's try the other equation. So let's plug in 1 for x, and let's plug in 3 for y. Does that equal 9? Well, 3 plus 6. Oh, yep. 6 plus 3 is 9. That is another true statement, which then means it's asking, is that ordered pair 1, 3 a solution to this system of equations? And the answer is yes. 1, 3 is a solution. On example 2, we're going to do a similar thing. Again, I'm going to plug in 5 for x and 3 for y into each equation. 6 times 5 minus 7 times 3, does that equal 1? Well, that's 30 minus 21. 30 minus 21 is 9. That does not equal 1. So we don't even have to check this other equation because it didn't even work in the first equation. So no, 5, 3 is not a solution. All right, example 3, we're going to actually save for class. And example 4, we're going to save for class. And I'm going to jump to example 5. And I want to see, but before I do that, I have to go back to example 4 and scroll down. We're going to be classifying linear systems. So we're going to talk about exactly one solution. That's where two lines cross at one place. When two lines are right on top of each other, that's infinitely many solutions. And when the lines do not cross, they're parallel, that is a no solution. Other names that you may hear is consistent and inconsistent. Consistent means there's at least one solution, and inconsistent means there are no solutions. So I'm going to be using those. Another name that I like to use, if I fix this, instead of consistent, sometimes an independent, in geometry, you call these intersecting lines. And when they're consistent and dependent, we call them coinciding lines. And when they're inconsistent, we call them parallel lines. Let's try that. It's not letting me write on the board here, so let's try that again. Right there. We call them parallel lines. All right, on example 5, what it's asking us to do is classify and determine the number of solutions for each system of equations. We may use our graphing calculator to check by looking at a graph. Otherwise, what we are going to do here is we're going to put both of these equations in slope-intercept form. So I have x equals 2y plus 6. So what I need to do here is I need to minus 6 on both sides. So then I get x minus 6 is equal to 2y. Divide everything by 2. So then I get x over 2 minus 6 over 2, which is 3, is equal to y. So my equation is y is equal to really 1/2 x minus 3. The other equation, we have 3x minus 6y equals 18. We're going to minus 3x on both sides. We're trying to get the x's on one side and the y's on the other. That's minus 6y equals negative 3x plus 18. Divide by negative 6 everywhere. We get y is equal to 3 over 6. That's like 1/2 x, and 18 divided by negative 6 is negative 3. Look at that. The blue line and the red line are identical. Because of that, we can write up here, they are the same line. They are considered coinciding lines. And so therefore, we are going to have infinitely many solutions because they're the same line. The other name that we can say, as we talked about on the last screen, is we could call it consistent. And we'll talk more about that and the correct way that I want you to talk about these in class. But when it's the same line, I like coinciding. All right, the rest we're going to do in class. Right now, pause the video, and I would like you to do these video questions in your notes.